Okay, as a follow-up to stoichiometry, the next most difficult thing to understand in general chemistry for most people is a concept called limiting reagents. Now, here's the thing. I actually already snuck it in the last video, so the concepts are already there. But we're going to look back in just a minute at how we talked about fruit baskets. But if you remember, we find out how many fruit baskets we could make in total by figuring out how much of each ingredient we have, and we are limited on the number of baskets we can make by the item that we run out of first. So whatever we run out of first limits how much product we can make, and we call this the limiting reactant. Okay, so we can deal with chemical problems the exact same way. It's just that it involves sort of math. So before we try any problems, let's discuss a few more definitions. So first of all, the theoretical yield is, in an ideal world, how much you can make. So you all know that if you go to make a cake, you can make the exact amount that it says on the box, if you're using a box, assuming. But in truth, there's like some of the batter that sticks to the sides, or maybe there's part of the cake that runs over the top. And the next thing you know, you don't have what you really thought you could make. Well, the theoretical yield is like the maximum you could ever make. The actual yield is how much you actually get. And this leads to percent yield. Percent yield is the actual yield divided by the theoretical yield times 100%. It's just a little formula. It tells you how much you actually got in a percent value in comparison to how much you could have gotten in theory. So when we're approaching these limiting reagent problems, we do the same thing that we did with the fruit basket. You determine the component one at a time as to what we're going to run out of first. That's going to give you your limiting reagent or reactant. Then you use that reactant to determine how much product can be produced, and that's the theoretical yield. Okay, so there's a little chart that I made that I hope we can continue to use. And really, it's even helpful in the previous videos worth of material. But I kind of think of when we're doing conversions in the format that you see here in front of us. Grand Central Station is kind of like going from moles of one substance into moles of another. Now, when I say this, I mean like how many apples do you need in a fruit basket? So that would be like the number of things of apples you have for a fruit basket. You need to do another one to go to oranges or bananas or whatever it may be. And moles is the Grand Central Station because that counts how many things we actually have. It's like a number that's representative of molecules. It's just a bigger package of molecules. Now, we could have different types of things that lead to these moles. We could start with molecules, we could start with mass, or we could start with volume. All of those things can lead us to the moles. And we can get there through either Avogadro's number, molar mass, or molarity if you're starting with a solution. So all of these things will lead you to the moles of A. Once you then try to look for whatever else you're looking for, like the product, how many fruit baskets can you make? That's going to give you your moles of B. We get this through the balanced equation ratio. And that's why balancing equations is so important. And the same thing happens when we get to moles of B. We can find the molecules of B, we can find the mass of B, or we can find the volume of B. And we do that by going through Avogadro's number, molar mass, or molarity once more. So just remember on this, you can only compare two things at a time, not more. So I'm going to keep copying and pasting in this chart so we can see what our map is going to be moving forward on each of the problems. But before we do that, let me revisit where we were with our fruit baskets. So remember, this was what a fruit basket consisted of, and this is what we had at the store. When we looked at the math that was involved, we had to do a few things. We had to figure out what those ratios were. Hey, guess what? Those are from the balanced equation. And then we had to compare things. When we compared things, we compared everything here to a fruit basket. All of these things were compared to the same thing. And in the end, what we found was that this only made 3 baskets. So we only got 3 fruit baskets because we only had 3 baskets to make them with. Once you ran out of baskets, you just have a bunch of fruit. So you can no longer make a fruit basket. So we're comparing everything to the same component. And this, the fact that we got 3 baskets led to 3 fruit baskets. That's the least amount of something that we had as a product. And so that means what our limiting reagent was number of baskets. So our theoretical yield in this case would be 3 fruit baskets. But you have to compare everything to the same thing. So in this case, we did it to the fruit basket. So let's apply that as we move forward. Okay, so now we're going to start with an example problem. We're going to react 2.5 moles of CuSO4 with 2.5 moles of BaCl2. And the question is, how many grams of BaSO4 will we get in the end? Now, this problem may not have come with an actual balanced equation. So that's the first thing that you've got to figure out how to do. So we're given hints in the problem. We know that we have CuSO4 and we have BaCl2, and our product will also contain BaSO4 as a solid. So you just have to look at what your positive and negative ions are, and we find that the last product will be CuCl2. The next thing we have to do is balance this equation. Luckily, this equation is already balanced because there's coefficients of 1 to 1 here. As a matter of fact, I tried to keep this a really simple problem for a reason. We're going to see more complex problems moving forward. So do not take it for granted that that is going to be a 1 to 1 ratio moving forward. You won't see that very often even. So you need to make sure that you keep track of your units and make sure you're doing your molar ratios in these. Okay, so we need to figure out how to get 3.25 moles of CuSO4 and compare that to the thing that they want at the end, which is grams of BaSO4. So if I'm going to highlight for you in red where we're going with CuSO4, we start with moles of, let's call that A. We end up in grams of BaSO4, so we're going to say that that's this, which means that we have to go through the route of moles of B. That tells me that what I need to get there is I need the balanced equation. We've already got that. But we also need the molar mass of B, which in this case is BaSO4. So that's the reason why I found this already. See how this is a great little trick? Okay. So I can start by saying we have 3.25 moles of CuSO4, and then I need to convert into moles of BaSO4. So this guy right here is taking moles of A into moles of B. And then I need to go from moles of BaSO4 to grams of BaSO4 because I'm doing this step right up here, and that gives me this many grams. Now, the other thing that I've been asked to do is figure out how many grams we can get from 2.5 moles of BaCl2. So in this case, this is the different one, and I'm going to highlight this in blue. Our BaCl2 is up here. It's the same thing. We're going to call that moles of A because this is a different scenario, okay? and we have to go into grams of BaSO4. So it's going to be the same pathway, but our ratio may be different. Okay, that's completely possible. So we start with the fact that we have 2.5 moles of BaCl2. We go to 1 mole of BaSO4 for every 1 mole of BaCl2, and then convert that to grams, and that's our answer. Now, in this case, we get less BaSO4 when we're using BaCl2. What that tells us is that you make less BaSO4 with BaCl2, so BaCl2, the thing at the beginning, is your limiting reagent, okay? And that means that this guy, the other one, is in excess, or excess reagent. And the theoretical yield is the smallest one. So that's our theoretical yield. In this case, we're not given an actual yield, so we don't have to worry about anything else because there's no other problem that is being asked of you. So you don't need to worry about that. But let's try another one where it does actually ask you for the percent yield. Okay. So in this problem, we're starting a similar type of reaction. We actually are still using the exact same balanced equation. But instead, we're going to start with something that's not in moles. So we're going to say that we're starting with 4.925 grams of CuSO4. And we have 5.0 milliliters of 2.5 molar BaCl2. You remember that molar is moles over liters. So that's got 2 units in it. And the question is how many grams of BaSO4 will you have as a precipitate? So I'm going to start, since we already have a balanced equation in this case, I'm going to start by highlighting sort of where on our map we are starting and where we need to go. So if I consider CuSO4 as A, I'm starting with grams. So I'm starting with the mass right here. I need to go from the mass of A into the moles of A, and I'm trying to get to grams of BaSO4, so I need to get over here, which means that I have to go from moles of A to moles of B. So in all these scenarios, I need stuff. So let's go back and look. I need molar mass of A in the first one. I need the balanced equations to give me the ratios in the second one. And I need the molar mass of B there too. So let's say that we're starting with this 4.925 grams of CuSO4. Just follow this path. As you go from the mass of A to the moles of A, we need the molar mass of CuSO4, which, oh, by the way, I got that already. So that's going to give me this step. Then as we go from moles of A to moles of B, I've got that ratio. Where did I get that ratio? From the balanced equation. Then I go from moles of B into mass of B, and I do that through that ratio right there. Where did I get that? Oh yeah, I figured that out as well before I started. And that's what led me to this value. Okay, now let's go back and look at another option. We start with 5.0 milliliters of 2.5 molar BaCl2. Now here's the cool thing. When you start with volume, you don't even need to figure out what the molar mass is, because we don't even need that when we're going over to moles of A. So in this case, we're still trying to get to the mass of B, which is BaSO4. And we still need to know what the molar mass is of BaSO4. We just don't need to know that for the BaCl2. So instead, I start with 5 milliliters of BaCl2. Now I do need to convert that to liters because keep in mind, molarity is moles per liter. So I do that by dividing by 1,000 to get it into liters and then taking it into account with our 2.5 moles per liter BaSO4. I then convert this, BaCl2 on that last one. Then convert this to moles of BaSO4, and from moles of BaSO4, I go into grams of BaSO4. And that tells me how much total BaSO4 I can make. Okay, so let me scroll this up if I can here. And what we find in the end is that this 2.92 is a lower amount. So this becomes our theoretical yield is 2.92 grams, and BaCl2 is our limiting reagent. Since we would make more BaSO4 with CuSO4, that means that it is in excess. So let's say you go into the lab, you try to complete exactly what it's saying. After completing the reaction, you get 2.65 grams of BaSO4. What's the percent yield? So you take the actual yield, you divide that by the theoretical yield, and you multiply times 100%. And you get 90.8% yield. That's actually a pretty decent yield. So that's pretty good. Okay, now, just like we did last time, if you get to the end and you have 1,500% yield, something is wrong. You can't have over 100% yield, or if you do find that you have something like that in the lab, maybe it's still got water in it or something like that. But usually you have a percent yield that's less than the 100%, because that makes sense, right? You can't recover more than actually exists. So there we go. Think about that when you get these problems underway. Okay. So here's our next problem. I really want you to pause the video and try this on your own without me helping at all. Once you're done with it, you can unpause and try and see if everything is correct. Okay, so hopefully you've already worked this problem, and this is just checking your answers at this point. So let's say you react 3.25 grams of CuCl3 with 1.5 molar AgNO3. Question is, how many grams of AgCl will you make? The first thing that I'm going to do is make sure that I have a balanced equation. So you start with CuCl3, you add AgNO3, that should give you AgCl, and the other salt should make CuNO3. Now, I said it's CuNO3 because this tells me that we're talking about copper plus 3. And so that's where this balanced formula came from. Then I need to make sure that the reaction is balanced, and I do so by adding 3s right there and there. So let's go back and do this sort of like I did last time. So I'm going to change this color right here to red so I can follow what's going to go on. I'm going to start with 3.25 grams of CuCl3. What I need to get to is grams of AgCl. So I'm going to say that's over here, which means that I've got to go all the way through this way. That tells me that I need the molar mass of CuCl3, because that's where I'm starting with. And I need the molar mass of AgCl. And so I figured that out already. I'm going to go ahead and show the way to get to the second one as well. So AgNO3. The difference is with AgNO3, we're starting with a volume. So we start down here, we go here, we go here, and then we're still going to compare that to the same thing. So we should go there. The thing that you're comparing in the end in both instances should be the same, because you can't compare apples to oranges, even though we've talked about fruit baskets, okay? You just can't do it. So I don't need any different molar masses in the second calculation because that's the same. So I don't have to worry about that. But you do have to worry about molarity, which is given in the problem. Okay, so I'm going to scroll down just because we don't have space and approach these problems. So in the first one, we start with 3.25 grams of CuCl3. I need to go into moles of CuCl3, and I do that through the molar mass. I then need to take into account that we have 3 moles of AgCl for every 1 mole of CuCl3. And finally, with the molar mass, we go into grams of AgCl. Now, keep in mind, and I haven't shown you this along the way, but all of these things should cancel out when you're done. And so if you have 3.25 grams of CuCl3, that should give you, in theory, 8.22 grams of AgCl. If, on the other hand, we are starting with 25 milliliters of AgNO3, we use the molarity that's given to us in the problem. And remember, this is in moles per liter, so we have to convert into liters. And that means that we're going to take that molarity in the third step instead of the second. We then have to take into account that we have 3 moles of AgCl for every 3 moles of AgNO3. Yes, those 3's cancel out, so you don't have to worry about it so much. But you do need to convert into moles of AgCl3. If you just put 1 and 1, since they cancel out, that's fine, but it's a good practice to make sure you just keep putting in the coefficients instead anyway. So then we go into grams of AgCl, and this is what you should get. And again, just to point out the fact that all of these should cancel out as you go through. So you end up in grams of AgCl. Let that guide you when you don't have the chart up here to use, okay? That will definitely help. So what we find is that this is the least amount of AgCl we can make between those two reactants. So this is our theoretical yield. That also tells me that AgNO3 is the limiting reactant, and CuCl3 is in excess. It is not always that the second thing that we do is in the theoretical yield. So just realize that I'm getting this number because this number is less than this value. Okay. So let's say that you isolated 4.92 grams of AgCl. What's your percent yield? You take the 4.92 divided by 5.375 times 100%, and that'll give you your percent yield. And there you go, you've got it. So you definitely need to practice these. If you haven't done so already, I'd advise going back to the beginning of the video and trying these 3 problems. They're a good practice for you for sure. Okay, thank you very much. I hope this goes well.